Hello, and welcome to the CPM webinar series. Today's topic is twin screw compounding basics. My name is Christian Davis, and I'll be your moderator for today's event. With locations around the world, CPM is a leading global supplier of twin screw extruders, extrusion systems, high performance replacement parts, ring extruders, thermal equipment, and supporting services. Our webinars are intended to service, support, and inform you about the latest technologies, maintenance methods, and trends in the industry. Presenting today's webinar is Karl Tietz. Karl has more than a decade of experience in the extrusion industry, from building to designing and manufacturing. As CPM's Global Extrusion Systems Director, Karl works closely with our customers to support mechanical, electrical, and process needs, among many other responsibilities. If you have any questions during the webinar, please type them in the questions field. If it's not answered, you'll receive a follow-up response by email. Karl, I'll now turn it over to you.
Thank you, Christian. Good morning, everyone. I first of all want to thank everybody for joining. And please, as Christian said, if you have any questions, please put them in the comments. So today we're going to just touch on what is twin screw compounding basics and just the basics of compounding and an extruder. So today we're going to talk a little bit about the introduction to compounding, an introduction and classification of an extruder, the modular design of extruders. Where does an extruder get its energy? Process variables during the extrusion process. We'll talk a little bit of torque versus specific mechanical energy. What are the basic things that limit the rate of an extruder, and then just basic scale up tips and tricks to just keep in mind. So without any more delay, we'll just get into it. What is compounding? Compounding, this is the process where mixing or blending of polymer additives in molten state lead to the creation of a desired product with a very specific desired set of characteristics. If you want to take it that way, compounding is almost like cooking food. To achieve the best flavor or taste, you have to have, a good recipe. And we'll refer to the taste and flavor as the property of your compound. Usually good recipes consist of three things. You got to have the right combination of ingredients. You need the correct proportion of each of these ingredients to go together. And then you need a really good, cooking procedure. So really good method. How this translates is in compounding, you need the right combination of products, raw materials. Each of these materials need to be in the correct proportion. And then the compounding process itself needs to be the right process to create a very distinct product with very specific characteristics for a very specific application. Now, if any of these three aspects are off, for instance, the ingredients or the proportions of the ingredients or even the cooking process, your taste or flavor of food is completely gone. Same with the compound. If any of these are off, your product does not have the characteristics and will not perform well in the application that you would like to use. So how are compounds made? Usually, polymer scientists and chemists develop formulations with a very specific method of preparation, which is your compounding process, to create a final product that meets a very specific set of properties for a specific application. And your product quality at the end of the day is controlled by these three aspects we talked about. You got to have the correct formulation. You got to have the correct proportion of each of the ingredients in the formulation, and then your process needs to be, the method of preparation needs to be correct. Otherwise, your product at the end of the day will not be what you expect it to be. So just to show you a little bit of what what the process looks like, you've got your polymers, you've got fillers, liquids, additives, depending on what your compound is made out of or your recipe looks like. Some of these ingredients can be in there, or all of them can be in there. They're usually mixed, put into an extruder, or the extruder does some of the mixing, depending on how your setup is. You form a strand or a pellet, and at the end of the day, you have a pellet that comes out and that can be reused in any environment. So now that we know a little bit more about the compounding, we'll move over to what is an extruder. Let's introduce you to an extruder. An extruder is a compounding extruder is a machine that melts, mixes, degasses, and forms your polymer into pellets with a very specific set of characteristics for predetermined applications. And as you can see here in the picture below, this is what a typical twin screw compounding extruder will look like. But there are different types of extruders out there, and there are three common main categories of extruders out there. One, you might have seen a single screw, heard of a single screw before. It only has one screw in the machine. Then you have a twin screw extruder where you have two screws and they have different configurations and are mostly modular machines. And most commonly in these are used in the compounding industry. And then you get multi-screw extruders where they've got multiple screws in the machine and they are designed for really specific environments. So how do we choose these extruders? And there's mostly one characteristic that sets them apart. So the characteristic is feeding. Some extruders are flood fed and some are star fed. So what does this mean and how does this apply? Flood fed extruders are usually single screw extruders, and it means that they only do the melting and the pumping of the material. It's already pre-mixed, and usually it is really determined by the product as to what the throughput of the machine is. So here you can see where the hopper is all the way filled up and the screw is fully filled, and the machine runs at a constant screw speed to give you a consistent output. So the output of this machine is determined by screw speed. The faster you run, the more output you get. The slower you run, obviously, the less. But also, for a single screw, if the pellet size increases or decreases from batch to batch, or you've got inconsistent product, your output rate will be inconsistent and your product quality will be inconsistent. And these are rarely used in the compounding environment. They're more used for melting and just forming pellets. Now, a star-fed extruder is more common in the compounding industry. And this means that there's another device that controls your feed rate into the extruder. When extruder is star-fed, the output of the extruder has nothing to do with the extruder itself. What do I mean by this? You can have a constant screw speed, and the feed rate can be changed up and down from minimum to maximum of the feed capacity of the machine. So you can have a real empty machine to almost star-fed to almost flood-fed machine at this constant screw speed, where with a flood-fed system, it doesn't work that way. The faster you run, the more output you get. In other terms, also, you can have a constant feed rate and you can increase the screw speed and decrease your screw speed, but your output would be exactly the same. It will just change the amount of energy input and residence time in the machine as well as the fill rate in the machine. This concept of star fitting a machine really gives you a lot of flexibility around controlling your process. That cooking process we talked about earlier, that's what we're talking about. You have more control and more variables you can change to control the aspect of your process in creating a compound. So with these different extruders, there are more categories, and we're just going to go briefly touch on them just to make sure everybody, if somebody talks about them out there, you have heard of them. But we will be focusing on twin screws mostly. So here are the three main categories on the left-hand side. You've got single screws, twin screws, and multi-screws. Twin screws are divided into two different types of twin screws. You get intermeshing twin screws, and you get non-intermeshing with twin screws. So what does that mean? Intermeshing twin screws are machines that share an area between the two screws to transfer material better and to create a better mixing environment. So you can see at the top where they're in the middle, you can see it almost running against each other on the root side of the element. That's where they intermesh. And then on the non-intermeshing, the screws are further apart and they just run next to one another. They don't run into one another. So when we talk about intermeshing machines, you get two types, a counter-rotating and a co-rotating machine. So on the right-hand side, you'll see Co-rotators are usually, they turn in the same direction, so both screws rotate in the same direction, where counter-rotating, the two screws turn in the opposite direction. And this comes down to application, and we'll go into this here in a little bit in the next few slides. The counter-rotator is also divided into conical and parallel. That's something we're not going to get into today, but just know that it's out there. And then non-intermeshing machines are only counter-rotating. They do not make co-rotating intermeshing machines. So focusing more on the twin screw and intermeshing and non-intermeshing. So here's a bit better example of what the differences are. In the top, you'll see the intermeshing between a co-rotator and a counter-rotator, and you can see how the two screws run into each other. With the co-rotator, you have two identical shafts and two identical screws next to each other that have the same pitch on the screws as they perform, where on a counter-rotating, they're the opposite. Due to the direction of rotation, you need to do this to be able to create the intermeshing part. The non-intermeshing machine looks similar to the counter-rotator due to it also being a counter-rotator, but you can see clearly how the two screws run next to each other. So non-intermeshing counter-rotating extruders are not typically used in the compounding industry. They have really advantages in the reactive extrusion, devolatilization of large volumes for solvents and monomers. So this is not typical extruder you'll run into in the compounding environment. So now we're doing the there's some extra slides here, sorry. So we're on the intermeshing counter-rotating twin screw extruders. They're more positive displacement pumps, and they have really limited mixing capabilities, and are typically used in the PVC industry. And then we have your full intermeshing co-rotating twin screw extruders, and they are really efficient in transforming energy into a melted polymer. They really do great in mixing, and the geometry really helps to make sure you get a good compound with most common types of extruders that we can use in the compounding industry. A little bit more about the intermeshing description, just to make sure we all, understand it a little bit better. Here you can see that the two screws are next to each other for the twin screw, and you've got the flight on the left-hand side and flight on the right-hand side. They're 90 degrees apart, and there where the two meet at the apex, you can see the intermeshing clearance and the intermeshing region. This is where the two screws intermesh and exchange material. You can see that it creates three different channels: channel 1, channel 2, and channel 3. These multiple channels are used to combine, mix, and melt a good compound and make sure that you have a consistent product at the end of the day. Now that we've talked about what an extruder is and the different types, and we're going to focus more on the twin screw co-rotating intermeshing machine, we're going to look a little bit more into the modular design of these machines and how it applies to compounding. The modular design of co-rotating twin screw extruders, it really provides a lot of flexibility to feed raw materials, inject liquids, vent at different positions, to create a really specific product for a specific application. The advantage of these machines are you can do a lot of different products on one machine, or you can use different machines to make the same product. It just depends on the configuration and the process you use. Usually the length of these machines and the configuration of the machines are determined by the product you're trying to produce. So what do we mean by these are modular machines? If you look at the process section, we'll start with the process section, where you can configure the process section as you need for your process. You'll see here you get feed barrels, and you get closed barrels, you get side feed barrels, and you get vented barrels. Now, these are 4 common barrels out there. Most extruders have these on them. There are more specific and really different designs on specific applications that you can get on barrels, but these are the most common you'll run into. So feed barrel you use to feed materials with, and the closed barrels usually you do mixing and melting in those sections. Side feed barrels are for adding additives or glass fibers if need be, and then venting barrels is to suck off all the air and all the volatiles that come off of your product. You can install these in any configuration. It's easy to change configurations on the fly with the machine you already have. And it all comes down to what product you're trying to make and how that recipe or how that process is to be applied to get your final product. These barrels come in different metallurgies as well. So depending on your process, if it's corrosive or abrasive, metallurgies can change in the machine for you to have the best machine for your application when it comes down to wear and tear on the machine. Another part that's modular in the machine is your screw configuration. So here's an example of a twin screw configuration. Usually you get conveying elements. So we'll start off with the common ones. You've got conveying elements, 1D pitches, 3/4 pitches, half pitches. These are usually used to create pressure, convey materials from the back to the front of the machine. And in changing the pitch, you get different applications as to reducing pressure or increasing pressure, or conveying faster, conveying slower, depending on what the application needs in that point. You also get reverse pitch elements. So it's a restrictive element. It pushes the material back in the flow direction to create a restriction for either increased energy or increased mixing capabilities. Again, all that comes down to what the process needs. Further elements that we use in a screw configuration are kneading elements. You get them in different configurations. For example, you get the 30-degree offset, you get them in different disc width, you get them in different settings like the degrees and 30, 45, 90. You have some of them are reverse conveying. These all have different effects, and some of them are more mixing, some of them are more shear creating. Again, depends on that process that you need to get to your final product. Here's a little bit better example of how these different elements influence the process. For example, if we take a 30-degree forwarding, it gets really good conveying rate, and it does help some mixing and shear input. It's just not a very aggressive element, so it'll help with mixing and melting, but it's not putting in a lot of energy. Where if you look at the 90-degree neutral, it's got no conveying to it, and it's got a lot of distributive mixing in it, less dispersive mixing, but also a lot of shear input. So this is an element you'll use to melt or create a lot of energy in your product where necessary. And then if you look at the 45-degree reverse element again, it creates a negative conveying rate. So it goes against, it's almost like an restrictive element where it pushes the material back. It creates really good dispersive mixing and puts in a lot of shear. So again, these are modular and you can stack them on your machine shafts as needed for an application. And what this does as well with the modular part is you can have different screw configurations for different products that run all on the same extruder. Again, you can do a lot of different products with one machine. A little bit more about a restrictive element. So the restrictive element has it creates in essence opposite flow. So you've got the flow direction, and then on the other side of the element, it pushes the material back. Over these elements, you create a lot of pressure, and it can create a lot of shear energy and a lot of energy input as well as mixing, because it backs up the material into your machine. It changes the fill of the machine in that section for a moment of time. So what about a complete process section modular setup? So here we'll look at a screw configuration with a barrel configuration. You'll see that we've got a feed barrel, and we've got on barrel 4 a side feed barrel. We've got on barrel 7 a side feed barrel, and then on barrel 9 we've got a vented barrel. And in between you'll see the conveying elements, the kneading elements, mixing elements, and on each part of this machine we configure it for a specific product. Here we've got a polymer and additives you feed into the feed port. Then we melt and mix it. Then we've added another side feeder that adds a filler with an atmospheric vent. You got to vent out some of the air in the machine to add some fillers. Then again, you've got mixing to mix in that filler with the melted polymer and additives that were fed initially. On side feeder 2, you've got glass fibers. Again, we're venting the air out. Then you got to mix that in again into your product to create a consistent product. And then we vent off with vacuum all your volatiles and air and moisture. And then at the end, you have your die, and it creates your product. Again, this can be set up in many different ways. The machine length changes, the amount of barrels you use will change, the screw configuration changes, all depending on the recipe you use, and the parameters of your final product you want to achieve. One of the things that the twin screw and this modular design really help with is controlling, quality of product. For example, your more sensitive products like your glass fibers, you can feed further downstream, as seen here, so it doesn't go through all that mixing and melting sections where it damages the glass fiber. So it's a more sensitive product, and if you have shear sensitive products that you want to feed and only need some mixing in, you can move them where you want, where you would like to put them in on the machine, and thus getting a really good product at the end of the day with just distributing all those characteristics correctly. Since the feeders control, the rate of a star-fed extruder, the feeders control your formulation, and this is where there are more than one product present, so you've got more than one feeder. And all of these feeders in combination together control your formulation and control your output. So it is really, really critical that those feeders are set up correctly, the recipe is put in correctly, and the machine is seeing all the materials at the right time and at the right proportions. Again, as we mentioned earlier, it's really important as to speaks to the aspect of having a good final product. If your formulation is correct, your proportions are correct, and your process is correct. So now that we've talked about what an extruder is, a little bit about how the modular design goes, where does our energy come from for this machine? So the energy sources are usually from 2 points. You've got the barrel heating, which puts about approximately 10 to 20% of energy into the machine or into your process. And the main motor of the extruder that usually puts approximately 80 to 90% of your energy into your product. And some of that energy can be removed with the barrel cooling system, so you can control the amount of energy you put into your product in various different ways. One thing I do want to point out that for a machine that is not fully filled, the barrel heating really doesn't play a big role in energy input due to the contact of the barrel. So the lesser filled your machine is, the less effect you see from the barrel on the heating. So this is just a little example of to demonstrate that. You can see the 3 little red dots. This is a machine that's not filled a lot, so the contact with the barrel is very minimal, and the energy input from energy transfer from the heaters are minimal to the process compared to the mechanical energy input. Here you can see an example of how the material melts in the extruder. So at the beginning here, you have the solid pellets. Then you have a partially melted polymer, so pellets and polymer. And then at the end, you've got a fully melted polymer. So this gives you an idea of what the length is. And just this is a small machine, so it's not big. And a bigger machine would obviously just have longer lengths. So we're going to look at a basic extruder process variables. And you usually have your extruder parameters, which are mechanical parameters like free volume, screw configuration, and your die geometry. Your process parameters are for screw speed, feed rate, and barrel temperatures. Through shear rate and shear stress, you get key system parameters like specific energy, which can be from mechanical and thermal. You'll see the melt temperature, residence time, and pressure in the machine, which will alter your molecular structure, and then at the end of the day, create a product with specific quality attributes. So you've got your physical properties, like tensile strength and impact strength, the rheology of the material, and then other aspects, other attributes are like color and the electrical conductivity, depending on what you're looking at. We're going to look a little bit at process variables. So what can we control? And if we do control it, what does it influence on an extruder? Here, we're going to look at screw speed. If you increase the screw speed, what is the result that you see in the machine? So if you increase the screw speed of an extruder, usually your fill percentage goes down. And this is assumed we keep the throughput the same. So your fill decreases, your torque will decrease as well. Your specific energy increases, which will show in your melt temperature. It will increase your melt temperature. Your pressure in the machine is reduced due to the lower fill. And then your residence time goes down due to a lower fill, and your dispersion of the product goes up. Another variable will be feed rate. So if we increase the feed rate and keep everything else consistent, screw speed and machine operating parameters. So if you increase the feed rate, your percentage of fill increases, the torque will increase, your specific energy will reduce, and we'll get into that here in a little bit as to why. That'll show again in the melt temperature. And then again, the pressure will increase, residence time decreases, and dispersion decreases. Here we'll look at the barrel temperature, how if we change the barrel temperature, it will influence the process. The percentage of fill will not change due to nothing really changing in the machine. The torque will go down due to a lower melt viscosity. Specific energy will go down because you're putting in more energy with the heaters. But again, these will be small changes just due to depending on the level of fill in the machine. Melt temperature can go either way or not change. Pressure will probably not change. Your residence time will not change. And the lower viscosity will cause less dispersion in the machine. Then if we looked at increased die pressure at the end of the machine, so sometimes the dies are downstream and you've got screen changers or melt pumps in between. It's more, if you create a restriction at the end of the extruder, in whichever way, if we increase that restriction, how does it affect the process? So you'll increase the fill percentage in the machine, torque will go up, specific energy goes up, the melt temperature will go up. Depending on where you measure the pressure in the machine, at the end of the machine, the pressure will go up as well. But in the rest of the process, it shouldn't change. Your residence time will go up, and your dispersion will go up due to product leakage over your flights. What if we increase rate and RPM of the extruder, so two variables at a time, consistently in proportion to one another? So if we increase the rate and the RPM consistently, your percentage of fill will not change. Your torque could change a little bit, but possibly no change if that proportion of increase is done correctly. Your specific energy will be consistent, your melt temperature will be consistent, and your pressure will be consistent. It does lower the residence time due to the higher feed rate, but due to the high RPM, your process stays consistent, and then the dispersion stays consistent due to the specific energy that you're trying to keep the same between low and high feed rates. So one of the things that shows here that really makes a big difference is the specific energy. I want to touch on the specific energy just a little bit because a lot of times that we confuse the amount of torque we see on the screen with the specific energy. So we're going to compare the torque versus specific energy to just talk a little bit about the difference and how, looking at the two different things, we can make certain conclusions. So while your torque is your torque percentage is an indicator of how much energy goes into the extruder, it doesn't necessarily show how much energy goes into your product. Since the torque only measures the main motor power, it doesn't really know how much energy or how much product goes through the machine. It's really hard to make any conclusions and say, well, this is for this product, this is the right torque for this result. The percentage of torque is more an indication of the mechanical limits of an extruder. So it shows you how close to the limit of the machine you run or how hard the machine is working for that specific machine. A better indication of what's happening with your material and your process is if you calculate the specific energy. The specific energy tells you more about how much energy goes into a specific amount of product. And that is translatable to quality of your product. And later on, we'll talk about scaling, and that'll help scale between different sizes of machines as well. So specific energy is the indication of energy input into your product that correlates to your final product properties. How is specific energy calculated? Specific energy, mechanical energy, are shown in units for kilowatt an hour per kilogram. And here's a formula of how you can calculate it. So your actual screw RPM divided by a maximum screw RPM multiplied by the motor's maximum kilowatts multiplied by the percentage of torque you see on the screen divided by 100. And if you have that, all of that, you divide it with your throughput. The value taken from, you can take the value from the motor or the gearbox, whichever one is less. You usually have about 3% losses through the gearbox, depending on how big the how much power, how much throughput you're running. That value gets significant or less significant. You can use either or. You'll be within a calculation framework. So I'm going to create a scenario here, two different scenarios, and to show you why calculating specific energy is important to understand what's going on in your process and not necessarily just look at the machine capabilities or the maximum machine capabilities. So we've got a sample A and a sample B. Sample A runs at 35% torque and sample B runs at 50% torque. You can't really tell anything from that information provided. So we'll, if we give a little bit more information, we'll say sample A runs at 900 RPM and sample B only runs at 600 RPM. Again, this information is not enough to relate anything to your process and how your product is performing, if you're running a good process for this product or not. You need a little bit more information here. So let's go to throughput. So sample A will run at 960 kilograms an hour and sample B runs at 1200 kilograms an hour. Now, if we calculate the specific energy of each one of these samples, you'll see that the specific mechanical energy of sample A is 0.154, and for sample B, it's 0.118. So here you can clearly see that during the conclusion of the higher torque sample, gets more energy is not true. there are, these three aspects to calculating the specific energy to understand what's happening with your product. So sample B that ran at 50% torque actually sees less energy, about 30% less energy per kilogram than sample A. So it's really important to, understand what you're looking at, understand what you're reading, and understand what you want to know. If you want to know the limitation of your machine, or if you want to know how good your process is and where your process is running. So this can be graphed just easily to show you guys. So here you can see sample A is with a lower torque, and actual more energy going into the extruder, where sample B has less energy, but it looks like, the percentage torque is more. So this is just a visualization of the scenarios I've created. So last but not least, we'll talk a little bit about, extruder rate limitations. Now that we know a little bit more about the extruder, the process, and just specific, a little bit more about the specific energy and how to look at where the energy goes. We'll talk a little bit about extruder limitations. Extruders will be rate limited by the amount of power that's on the machine, or by the amount of product you can physically get into the machine, so volume limited. These are most commonly in the compounding applications. There are other factors that might influence what the rate limitations are, but these are the basic rate limitations you would run into in a compounding environment, and you'll see them mostly out there. Mostly as a generalization, most polymer applications run with a specific energy, mechanical energy, between 0.15 and 0.25. There are differences. There are differences in different products, and it may vary. So there are exceptions out there, but this is what you'll commonly see. Some twin screw machines can run up to 1,000 RPM. So it can be really high, a high-speed compounding application, but very few compounding processes run at these high speeds due to the degradation of your material you run into. Any product that you run glass fibers in, you try to avoid anything above 600 RPM, just due to the degradation of your fiber, which influences the characteristics of your product at the end of the day, which are not desirable. So that would be a limitation on the rate for adding glass fibers. Again, your final melt temperature will increase with the screw speed. So the faster you run, the higher your temperature is. So you gotta be wary of degrading your polymers. Most polymers are degraded when the product temperature gets way too high, and usually these are results of products run between 600 to 900 RPM. And then if you've got thermally sensitive products running above 300 RPM, depending on the sensitivity, is a challenge. The length of the machine doesn't really influence the feed rate limitation. Where it does have an impact is in reactive extrusion, or for highly filled polymers. So if you fill more than 40%, on your polymers, you'll need 2 side feeders, and for that, you'll need more mixing length. So your machine needs to lengthen out a little bit, but it does not have a straight up effect on the longer the machine is, the more product you can run. There are not really any models out there that can predict a certain amount of powder being put into a machine, and what the limitations are on that. Bulk density really doesn't play a role too much in helping to size your extruder, but it does make a big difference in the feed limitations. For example, it depends on how you feed the powders. Usually if powders fall from a high distance down from a mezzanine feeder down to the side feeder, if it's a meter or 2, a few feet, it aerates, and then your bulk density goes down, and then it creates feed limitations on side feeding and how much filler you can run on the machine. And then the length of the extruder also is determined by your process requirements. So where you can feed and cannot feed. So if your machine is not set up correctly and you got to feed a lot of powders and you feed port instead of downstream, that creates process limitations. And then you'll always try to install as much power as you can onto a machine for you to be able to use as much as you can, unless there's a very specific reason you don't want the big motors on there. But it's really the case where you put on a smaller motor just because you don't want the throughput. Usually a different machine would be the option. So there's a little bit about rate limitations for a machine. And last, we'll look at some scale up, some basic scale ups. The goal for a scale up is to reproduce your energy, time, and temperature on a larger machine. So if you've got a small machine and you want to do more throughput, but you want to run the same product with the same specifications and the same characteristics on your final product, you want to reproduce that energy, time, and temperature. And for a twin screw, there's really a big advantage and scale up. So you want to duplicate the energy. Your physical properties are always a result of the energy, time, and the temperature of your product. So again, the specific energy, if you know what the specific energy of your small machine is, it's easy to scale it up on a big machine and get it to say, this is your specific energy on a big machine. This is the throughput the machine can achieve. There's a range of specific energy, specific mechanical energy that can produce acceptable properties and good properties. And usually this is called the process window. So you don't have to stick to exactly that number. It can vary a little bit depending on your product and your configuration of the machine. If we look at basic volumetric scale up, for a volumetric scale up, machines of the equal DODI ratio, the ratio diameters, assuming your length is the same and assuming your constant speed, your geometrically equivalent in screw design, the scale up becomes fairly easy from the volume aspect of size. So using the volume scale-up factor, you will reproduce the degree of fill, the residence time, and the average shear rate for machines of equal DODI. Now, can I scale up between, volumetrically between different DODI ratio machines? Yes, you can. It is a little bit more trickier. You got to take a little bit more into consideration due to the volume difference of the machine. But mathematically, it is possible. We're going to look at constant shear rate. So constant diameter ratio, so the DODI is constant. This will create a constant shear rate. Machines with a constant diameter ratio will produce equivalent shear. So if they've got the same DODI, you'll have the same amount of shear rate and the same amount of degree of fill as we mentioned in the volumetric scale up. And if you assume a constant screw speed and a constant screw configuration, you can easily calculate the required matching size machine for it. One thing that's to be noted is the larger the machine gets, the larger clearances get on the machine between the barrel and the screws. This influences the calculations, but can be taken into account. And you can scale up from small machines to bigger machines. What we try not to do is we try not to scale up from a lab machine to 177 millimeter, for instance, from a really small machine to a very, very big machine, just due to those clearances become significant in the shear rate change of the machine, and it'll influence the process quite a bit. So you try to scale up as close as possible to the next size machine or two sizes up in machinery. Again, average shear rate decreases with increased diameter just due to the larger clearances in the machine. Then scale up on power limitations. Scale up factors are based on available power. So typically, this follows a scale up for machines similar to the same DODI, and we assume a constant screw speed again. Your volumetric scale up reproduces specific energy. It does not reproduce performance torque if machines are different in torque density. So you gotta have the machines gotta have the same torque density, or at least the maximum allowable torque density to be the same. Scale-ups become problematic when machines have different torque densities, so power to volume. It's not impossible, or a big problem no, it is a problem in doing the scale up, but it's not not doable. Common problems with scaling from an old machine, from a newer machine to older machines. They usually have lower power on them, and the newer generation machines have higher torque density, so your throughput between the old 92 and the new 92 might be different just due to that power difference. This results in a deviation for volumetric scale up. So if the power is less for the same volume of the machine, it changes the dynamics of the extruder, and then the scale up gets difficult. For example, if you're running on a machine that is 8 times larger with only 5 times the power, the degree of fill is lower. You've got a longer residence time, and the shear, you've got higher shear rates, so your product is different. Your specific mechanical energy input changes. But there are ways to compensate for all of this, and scaling up on a twin screw is fairly easy from one size to another. If your DO/I ratios are the same, it just makes it all that much easier. And if the specific mechanical energy of the product you want to run right now is known, it's really easy to scale up to a bigger machine with the same DO/I ratio. That being said, this is all for today. Thanks for joining again. If there are any questions, please let us know.
Thank you, Karl. We did have a couple questions. What is the ideal clearance between screw flight and barrel wall?
So that depends on the machine and the OEM manufacturer. It depends on the size of the extruder. It has to do with how you install it, and what is possible on the bigger size. So on a small machine, you can have small clearances because you can install it easier, where on bigger machines, you need more tolerance to get it in there. So it really comes down to the manufacturer and what they're comfortable with doing with that clearance.
Okay, great. And then what sort of steels are used for screws typically?
So again, these are vague answers because it's really hard to answer. It depends on the application. You can get an X260, you can get a 10V-12, you can get 440C, you can get nitrided, and we can get through hardened. So it really depends on what you're running, what kind of compound you're running, what the products are that influence metallurgy. If you have more corrosive than abrasive wear or more abrasive than corrosive wear, there's really a big selection of materials out there that you can use on a machine.
Okay. And can raw material properties affect the specific energy?
Depends on the property. So would the bulk density necessarily change the specific energy? Depends on how much it changes, but I doubt that the bulk density would change it. But if the melt flow changes from one polymer to another, that definitely changes the specific mechanical energy. So it really depends on the character of the difference, or on the specific product that is different.
Okay. And then last question, what is the formula to work out the throughput of the twin screw extruder?
So the formula to work out the throughput is all the feed rates of your feeders that put material into the machine. The twin screw setup as material in equals to material out. So you totalize all your feeders and whatever you're injecting, and that's your total throughput.
All right. Well, Karl, thank you so much. And to everyone who joined us. A recording of this webinar will be available on 1cpm.com within the next week or two, where you can also find all of our previous editions as well. This concludes today's webinar. If you have any questions or would like more information or perhaps some copies of these slides, please feel free to email us at extrusion.sales@cpm.net. Thank you, everyone.